In this video, we're going to look at Simpson's rule. The trapezoidal rule approximation that we looked at in the last video applies straight line segments and adds up all the trapezoids to estimate the definite integral from a to b, f of x dx. However, a more accurate technique known as Simpson's rule fits a quadratic function, a parabola, to equally spaced data points. And we can tell right off the bat that this is going to be more accurate because we're estimating a curve with a quadratic function with a parabola, estimating a curve with another curve. All right, so what we do is we start with the interval AB, and our delta x is the same as before. It is b minus a divided by n, xi. The equally spaced x values are a plus I delta x. I goes from 0, 1, all the way to n. And the first x value is a, and the last x value, xn, is b. And we need an even number of partitions for the Simpson's rule. So n has to be even. All right, we're going to look at the proof of the Simpson's rule. So we're fitting a quadratic function to these pairs of data points. We're going to compute the coefficients a, b, and c such that a parabola goes through these 3 points. So when x equals minus h, the y value is y0. Plug this into the quadratic function, and we get y0 is equal to ah squared plus bx, that's minus bh, plus c. That's equation 1. Now x equals 0. X is 0, y is y1. Plug it into the quadratic function. We get y1 is equal to a times 0 squared minus b times 0 plus c. So what we get is c is equal to y1. Now let's plug in x equals h. X is h, y is equal to y2. Plug it into the quadratic function, and we get y2 is equal to a times h squared plus bh plus c. Now, if we add equations 1 and 3, we will get, well, on the left-hand side, we get y0 plus y2. So what we get is y0 plus y2. What about the right-hand side? On the right-hand side, we get ah squared plus ah squared. That gives us 2ah squared. We get minus bh plus bh. It cancels out. That gives us 0. And we have c plus c. That gives us 2c. So let's isolate 2ah squared. That is going to be equal to y0 plus y2 minus 2c. But we know from before that c is equal to y1. So we get y0 plus y2 minus 2y1. Let's rearrange this. We get y0 minus 2y1 plus y2. And c is equal to y1. So now let's compute the area under the fitted parabola from x equals minus h to x equals h. So integrate minus h to h, the quadratic function ax squared plus bx plus c. Integrate with respect to x, reverse the power rule, integrate term by term. We get ax cubed, divide by 3, plus bx squared, divide by 2, plus cx. Evaluate it from minus h to h. Apply the fundamental theorem of calculus, putting the upper limit in, we get a h cubed, divide by 3, plus b h squared, divide by 2, plus ch, minus, put a lower limit in, we get minus a h cubed over 3 plus b h squared over 2 minus ch. Now let's subtract these, distributing the minus sign, and when it's all simplified, we get 2a h cubed divided by 3 plus 2ch. So what we have shown is the integral from minus h to h, ax squared plus bx plus c integrated with respect to x, that's equal to 2a h cubed divided by 3 plus 2ch. Let's factor out h over 3 from every term. So h over 3 is factored out, and we get 2a h squared, and we get 6c. We have to place a 6 because 6 over 3 is equal to 2. Now from before, we know that c is equal to y1, and 2a h squared is equal to y0 minus 2y1 plus y2. All right, so what we have is the integral from minus h to h, ax squared plus bx plus c, integrated with respect to x, that's equal to h over 3 times 2a h squared plus 6c, and we solved for these constants in terms of the y values, so we get h over 3 times y0 minus 2y1 plus y2 plus 6y1. Let's rewrite this. We get h over 3 times y0, and here we have minus 2y1 plus 6y1, that gives us 4y1 plus y2. Now let's add up the areas under the quadratic functions over all the pairs x0, x2, x2, x4, x4, x6, and lastly xn minus 2, xn. So basically, just as with trapezoidal rule, we were adding up trapezoids, with the Simpson's rule, we're adding up the areas under all of these quadratic functions. So what we have is the integral from x0 to x2, f of x dx, plus integral from x2 to x4, f of x dx, plus integral from xn minus 2 to xn, f of x dx. Now we show that the area under the first quadratic is h over 3 times y0 plus 4y1 plus y2. Similarly, under the second quadratic, the area will be h over 3 times y2 plus 4y3 plus y4. And all the way to the last quadratic, we get h over 3 yn minus 2 plus 4 yn minus 1 plus yn. If we simplify this, we're going to get h over 3 times y0 plus 4y1 plus 2y2, because you have y2 and y2 here, 2y2, plus 4y3 plus 2y4. So you can see the pattern, 1, 4, 2, 4, 2, 4, 2, plus 2 yn minus 2 plus 4 yn minus 1 plus yn. So there is a pattern. We have 1 here, 1 y0, 1, 4, 2, 4, 2, and the one before the last ends in a 4 and a 1. So you can think of it as a 42 rule, basically. So let's rewrite this. We get delta x over 3 times y0 is really f of x0, isn't it? That's f of x0 plus 4 f of x1 plus 2 f of x2 all the way to 1 before the last, we get 4 f of xn minus 1 plus f of xn, and we close the bracket. That's the Simpson's rule. All right, so let's do an example. Apply Simpson's rule with n equals 4 partitions to integrate, to estimate the integral from 1 to 2 f of x dx. And in this case, the function is 1 over x. So the solution is the function f of x is equal to 1 over x. We have 4 partitions, n is equal to 4. Delta x, the partition width is b minus a over n, 2 minus 1, divided by 4, 1 over 4, that's 0.25. So we have our equally spaced x values at 1, 1.25, 1.5, 1.75, and 2. So the integral from 1 to 2, 1 over x dx, this is approximately equal to S4. That's equal to delta x, which is 0.25, divided by 3. F of 1, evaluate the function at the x value of 1, plus 4 times f of 1.25. Evaluate the function at 1.25, plus 2 times f of 1.5, plus 4 times f of 1.75, and lastly, plus f of 2. Now the function is 1 over x, so let's evaluate this. We get 0.25. Divide by 3, f of 1 is just 1, plus 4 times, what is f of 1.25? Well, the function is 1 over x. That's the function, so it's going to be 4 times 1 over 1.25, plus 2 over 1.5, plus 4 over 1.75, and the last one will be 1 over 2. If we plug this into a calculator, the Simpson's rule approximation to this definite integral is going to be 0.69325. That's the Simpson's rule approximation to this definite integral. Now, notice the definite integral from 1 to 2 f of x dx, can be computed exactly by using the fundamental theorem of calculus. The integral from 1 to 2, 1 over x dx. What is the antiderivative of 1 over x? That is ln x, log x. Evaluate it from 1 to 2, apply the fundamental theorem of calculus, we get ln 2 minus ln 1. Log of 1 is 0. So the answer is log 2. This is the exact value of the area under the curve. And that comes out to 0.69315. Let's compute the error for Simpson's rule, S4, and compare it to the exact value. So S4, the Simpson's rule approximation with 4 partitions, we computed that to be 0.69325. We applied the fundamental theorem of calculus to calculate the exact area under the curve under the function 1 over x, an integral with respect to x. That came out to be 0.69315. So the area of the Simpson's rule is the exact area under the curve minus the approximation. That's 0.69315. That's this number here. Minus the Simpson's rule approximation. That's 0.69325. And that's what we found here. All right, and if we calculate this, the error Simpson's is going to be the integral from 1 to 2, 1 over x dx, minus S4, and in absolute value, that's going to be absolute value of negative 0.0001, and that's just going to be 0.0001. That's 1 over 10,000. So it's a very small error. So the error of approximation is very small with n equals 4 subintervals. Let me put this in, subintervals. And the error, the absolute value of the error Simpson's, is 0.0001. This is why this is a really good technique, because it gives us really accurate results with very small errors. This error is 1 over 10,000. All right, thanks. Oh, I have one more page to look at. So this is basically the review. So what we have is Simpson's rule, the integral from a to b, f of x dx. The formula is Sn is delta x over 3 times f of x0 plus 4f of x1, 2f of x2, 2f of xn minus 2, 4f of xn minus 1 plus f of xn. So think of it as a 42 rule, 1, 4, 2, 4, 2, and so on. N has to be an even number. This is the only restriction with the only restriction with Simpson's rule is that you need an even number of partitions. So xi is a plus I delta x, and that's your equally spaced x values. I ranges from 0 to n has to be even, and we talked about the pattern. And so another way of writing this formula is Sn is delta x over 3, y0 plus 4y1, 2y2, 4y3. 1 before the last has to end in a 4, and the last one is just 1 times yn. All right, thanks.